Okay, guys. Now, recording is in progress. Welcome to our class today, Thursday, February 17, 2022. Yesterday, we don't have a class due to, very low number of attendees. And they informed me that you have a midterm. I hope that you did well. However, today also is very low. I don't know what is going on. Only 21 students are logged in the Zoom meeting. However, we shall continue. I cannot wait more. Another thing that happened during the weekend, I will announce the list of group assignment because I received multiple groups. There were 3 or 4 students, some individuals, 4 students, they don't add their name to the sheet. We added them as individuals. However, they will get a penalty, a mark deduction from their assignment because despite several reminders during the classes and also through the announcement with the deadline, they ignore all of those. So it's their call. So they will get a mark deduction because they don't follow the instruction. At all, I will announce we merge some groups together. Those of 3 or 4 students we add, some group we add individuals. So we have like, I'm not sure, just give me a sec to check how many groups we have now because the TA did them and do the merging. Okay. Yeah, we have 22 groups. 15 groups have 7 members and 7 members, and 80 groups have 8 members. So they become 9 groups, I think. We have 6 groups of 7 members and 9 groups of 8 members. So this would be regards group assignment. As I mentioned before, that once we release the assignment, we'll talk about it. That the assignment also there's anybody who's not responding or answering emails, who did not do his part. So we need, after the cover page, like each one what he or she did. And those who no response, just put beside their name no response. Don't be shy, and only one group member will submit the assignment. We don't need multiple submission for the same assignment because this would turn it in, will cause that there is a plagiarism, and then we have to go back to the first submission. So one submission per group. One group member will submit his assignment or her assignment instead or in behalf of the other group members. And since the names and ID is there, then the TA, when he mark the assignments, he will add the mark. It will be equal. But if some group members, they are irresponsible, they don't answer, they don't participate with you guys, just beside their name what he or she did, not responding or irresponsible or not responsible or no action, whatever, then he or she should get a 0. I hope not. I wish that there is no conflict or no misunderstanding between the group members. However, if there are some group members they don't want to do the work, the other group members will do the part he or she should do, and just let me know that he did nothing, and I will take care, and he will get or she will get a 0. It's happened last year. Few students, like out of 148 students, 3 or 4 In some groups, they were not responsible, and I don't know. It's their call. They don't mind to get a 0. Okay, now we stop. Let me share my screen. We stopped last class here at pumping lemma for context-free languages. So the pumping lemma here for context-free languages, a bit, it's the same concept, the same pigeonhole concept. However, you will find the difference that we will split the string that we have to 5 parts instead of 3 parts. This handout is a final exam material. It will not be part of the midterm again. And guys, don't forget tomorrow the tutorial. It will be in person. It will be in person if you have a question, and also the TA will deliver many examples about pumping lemma, about deterministic finite automata and undeterministic. Those examples would help also to submit your assignments, to do your midterm. If you have any question, you can ask, feel free to ask the TA. So tomorrow from 8:30, I believe, to 10:30. Wish you the best of luck. Attendance is not mandatory. However, I would advise everybody to attend the tutorial. Okay, so pumping lemma for context-free languages. Non-context-free languages, consider the language L, a to the power n, b to the power n, and where is greater or equal to 0, which is the same example Okay, you have an interview. Yeah, the presentation that the TA will deliver, I will post it in OWL. I'll make another tab like a class note, which is tutorials. And the PowerPoint or the presentation of the tutorial, I will post it in OWL. But if the student asks questions and the TA answer them, they are not part of the PowerPoint presentation. So many students, they told me always their feedback that it's very beneficial. But if you cannot attend it, at least what the TA will deliver in the class or in the tutorial, it will be, the presentation will be posted on OWL, which has many examples. So don't worry. You are welcome, Colin. Now, as we mentioned, if you remember, it's almost the same example like 0 to the power n, 1 to the power n, where n is greater or equal to 0. And we proved that using pumping lemma that it is not a regular language. We proved that. And in the book, in the handout, in the class note, we do the example, this example multiple times. We proved this language non-regular, using the pumping lemma for regular language. And the result of our study thus far has shown CFGs and PDAs, guys. I don't know why, Professor Essex, you call it PDF. It's push-down automata. So we used to have PDA, and you will find in the class note, it's a PDA. No, the assignment 1 is individual, Taylor. Assignment 1 and 2 are individual. Assignment 3, which is the last assignment in the term, would be a group assignment. So when I'm talking about the group, I'm talking about what we call it a group assignment, or you can call it assignment 3. But 1 and 2 is individual. Each student should submit. Clear? Yeah. I don't know why he called it PDF. I'm not sure if there is another, it is abbreviate another like phrase, but what we used to have it PDA, push down automata, are capable of some form of counting but just how many things can CFG or PDA keep track of? This is the question. Now consider another language, L prime, that has A to the power n, B to the power n, C to the power n, where n is greater or equal to 0. Now we need to keep track of 3 things. We said that for 2 of them, that the pushdown automata or context-free grammar, they have like some kind of a count or counts. But what we will do with this one when we need 3 counts? Because it's easy to make sure that A to the power n and B to the power n, I can push in the stack, then for each B I can pop 1, then I can make sure with the stack, as we take in the previous classes, that there are A's and B's are equal, then it will be a context-free grammar. We can prove that. But what about this? When we have a 3, is there a CFG or PDF or PDA that can generate or recognize? Try to memorize this word, recognize, because in the coming few handouts we'll use language recognition and recognize A, recognize L. We will talk about, or you will hear this term recognize a lot. L prime, it seems like no. Recall our solution to L was to push all the A's on the stack and pop them off to match each of the B's. But this is for L here. Then we can know that the number of A's equal number of B's, then the language could be a context-free. But we're left with empty stack. So now we can compute or compare C's if there is nothing left in memory to compare to. So when I reach to C, I'll compare it with what? So this is a problem. So with the stack solution that been used with pushdown automata and context-free grammar, we cannot compare 3 things. We can compare 2 things as maximum. So here we will introduce the concept of parse trees. What is the parse tree? Why we use it? Let L be a language and let S belong to L, be a string. If L is context-free, there exists some context-free grammar to generate S. We can derive S beginning with a start variable S and substituting variables or terminals according to the grammar until only terminals remain. And we use this like S, and we keep going on, and we fill in this one. Now, recall in the pumping lemma for regular language, if a string was long enough, then by pigeonhole principle, it must revisit a state within the automaton, forming a loop. Because we said with pigeonhole that we need at least n plus 1, which means that there one of the state will be visited twice at least, which form some kind of loop. Let's extend this idea to context-free grammar. Setting if a string is long enough, then by pigeonhole principle, it must revisit a variable somewhere during the derivation. Now, let's have this example, and we'll do the parse tree together. Consider the following grammar. We have S, it will give me ATB, T will give me ATB or epsilon. Suppose we wanted to generate the string AABB under the following derivation. So at the beginning, we'll move from S to ATB, then we'll move to the T will replace it with ATB again, then the T will be replaced at the 3rd time with epsilon, it will be AA epsilon BB, then we will have AAB. The variable T was repeated, that is t is substituted for something that led to another t. And like in the pumping lemma, for regular languages, we can pump this loop and the result should still be in our language, which means once we replace the t, then we replace it again, then this situation that we have a loop, we revisit the same thing. With pigeonhole concept, then we can pump this loop and the result should still be in our language. Let's see. This diagram depicts a loop. For example, variable t that follows a derivation leading back to t again. The resulting string s can segmented into 5 parts, u, v, x, y, z. You remember in the first pumping lemma, for regular languages, for how many parts we divide the string? 3. Yes, thank you, Gareth. It was x, y, and z. Now, here with context-free grammar, so be careful in the final exam. When I ask you context-free grammar or a push-down automata, then you have to use the 5. When I ask you not regular, using pumping lemma, prove that the following language is not regular, then you have to divide it to 3. So you have to differentiate between not regular or non-regular languages and context-free grammars. Notice the outcome of the T to T loop is strictly contained a substring V and Y. So if we have the first thing S here, then we have, as you remember here, ATB, then we have the first T, then we replace the another T with ATB again. So we have the T twice. Then, so here we choose that the first thing is U, the second V, the third is X, the fourth segment is Y, and the fifth segment or partition is Z. Okay, so what happens if we substitute one of the T's with another TT derivation? Pump once, we add another T, we pump it once. What will happen? So we'll have U, V, X, Y, and Z again, as we see. So if S equal U, V, X, Y, Z, and V and Y are the result of T, T to T derivation, then if we repeat pump the T segment to something of the form TTT, and we can replace this with epsilon, then the V and Y section will be repeated. So it will be U, V, V, X, Y, Y, and Z. If L is a context-free grammar, sorry, then S prime must be a member of L. So 2 must S double prime U, V, V, X, Y, Y, Z. Similarly, we should be able to remove the TT segment and hence V and Y substring and still have the result be a part of the language. So if S equal U, V, X, Y, and Z belong to L and L is a context-free grammar, then it must also be a case that S prime with U, V to the power I, you remember VV, then we pump it, I, X, Y to the power I, Z belongs to L for all I greater or equal to 0. If you remember, in the non-regular language, we just pump the Y. Here we add the U, V, and we pump the V again. Okay, guys? Pumping lemma for context-free languages. The definition. If L is a context-free language, then for all string S belong to the L where the cardinality of S is greater or equal to B, the pumping length, then S can be divided into 5 parts. S equal U, V, X, Y, and Z, where U, V to the power I, X, Y to the power I, Z belongs to L for I greater or equal to 0. The cardinality of Vy is greater than 0, so V and Y should not be an empty or epsilon. Vx and Y less or equal to P V, X, and Y is no greater than the pumping length. This diagram, so example, counting three things. From now, I'm telling you this is not a context-free grammar because I proved to you that by the stack, I can compare A and B, but when I reach to C, if I push the C to the stack, how I'll pop it out? There is nothing to compare with, right? So this is not a context-free. A to the power n, B to the power n, C to the power n is not a context-free. How will you prove that? Another one, use the pumping lemma for context-free language to prove that the following language is not context-free. WW, where W belongs to 0 and 1 star. So those we'll prove them. We'll have some example to prove them using the class notes. Here, Professor 6 was like depending on the textbook to read it from the textbook, how to prove those, but no, we'll prove them. Now, language classes. We looked to the language classes at the beginning of handout. We have looked at both counting and the string copy languages. Here is a table showing the capabilities limitation of each language class. If we have a regular language, can't count and bounded. We don't have a counter. Can't copy. If we are at context-free, then we can count two things. We can't copy forward, can do like WW to the power R. Context sensitive, which we said it's beyond of our course, this can count for things, A to the power n, B to the power n, C to the power n, and D to the power n, single copy of WW, but this is beyond our course scope. Recursively enumerable, unrestricted A to the power n, etc. Unrestricted WW, which one? And this way using the Turing machine, and we'll see it in the some coming handouts. Questions still here before we start class note 9? Did I upload the class note 9 to the OWL, guys? I'm not sure. Yes, we uploaded. Okay, let me open. Which one? This is 8, 7. Yeah. Yes, this we done. And with 8, we said 8 is not part also of the midterm. We talk about this, Pushdown Automata, we prove those, PDA and DFA, the stack, examples, we took this as example. Yes, I remember this, and this. Yes, so 8, we are done with 8, so we will start with 9. With 9. Parse tree. Let G be a CFG and W be a string belong to L. So here are example of parse tree, and then we'll have the pumping lemma. Okay, guys. Yes. Okay. Let G be a CFG, context-free grammar, and W is a string belong to that grammar. A parse tree of W with respect to G is a rotated ordered tree. that represent the derivation of W with respect to G. And as of now, we'll use WRT, which abbreviate with respect to. Synthetic structure of W with respect to G. Now, example, if we have the following grammar, S send us to 0 as 1 or epsilon. If we have W equal O to the power 3, 1 to the power 3. Parts of W with respect to G is S 0 as 1, then this S we replace it with 0 as 1, and this S also we replace it with 0 as 1, then S become epsilon, so we have 0 0 0 1 1 1, which is 0 to the power 3, 1 to the power 3. So what is the properties of parse tree? The parse tree properties: every internal node is a variable, every leaf node is either a terminal or epsilon. If it is epsilon, then it is the only child of its parent. Here, this is the only child of the parent. If not epsilon, then I should have 3 childs. If an internal node is labeled R and A1, A2 to AK are the children of R from left to right, then R will lead us to A1, A2, AK is a rule in G. Concatenation of the leaves of the parse tree from left to right gives the string W, as you see here, 0 0 0 1 1 1. Left, then right. Another example. Assume that we have the following grammar. S will lead us to 0 as 1 S, or 1 as 0 S, or epsilon. So if we have here 0 1 0, okay, so we'll have S, then here 0 1 0 as 1, here S. The S here will become an epsilon because we have the 0 1, we need those. Then the second S, we will again make it 0 as 1 S. So it will become 0 1 0 1, so this is epsilon. Then the other S, it will be 1 S 0 S, epsilon epsilon. So we have the following 0 1 0 1 1 0, 0 1 0 1 1 0. This is the thing that we have. This is the parse tree of W with regard to G. Here you can do 0 1 0 as 1 S, and here you can make 1 as 0 S, 1 as 0 S, and those with epsilon. Then you start reading from left to right, it will give us the same string. This is another option. We can have multiple parse tree for some strings. This is what we wanted to prove. This is the rooted tree with roots. We start at 1, then the root can expand. Is that clear? Okay, good. So this method in computation, we call it top down. We start with one thing in the top and we go with the roots till we reach to our final destination. There may exist multiple parse trees for a string with respect to that grammar. For example, our example 0 1 0 1 1 with regard to G2. Question: what about G1? Can be multiple parse tree? No, the rule make it unique variable, 0 as 1. This is our example 1, which is 0 to the power 3, 1 to the power 3. For the levels, it depends on how the grammar is designed, how these grammars are designed. So we don't know. As I told you, some of them, they have multiple parse tree. I'll ask you about one of them in the exam. Some of them, no, they have a single tree. So how many levels? It depends on the expression and the string. So with the same context-free grammar, I might have 5 levels for certain string. Some of them I need 2 levels. For example, here, if I make it, in this example, where it is, this one, if I make it 0, 1, 0, 1, then we'll have less level, right? But if I make it 0, 1, 0, 1, 1, 0, 1, 1, 1, 0, it will be more levels. So it depends if what is the string I'm asking you about, and also depends on the grammar itself here. And it depends on the grammar itself. Okay, Amanda? What do you mean by how many times?
Can you scroll up to example 2?
Here?
Yeah, so
Yes.
yeah, so here, how do you know, actually, can you scroll up?
I know based on this string I'm giving to do 0, 1, 0, 1, 1, 0. Okay, here they gave me 0, 1, 0, 1, 1, 0. This is the string, so it depends on the string. But if I got like 0, 1, 1, 0, 1, 1, 0, 1, 1, I don't know how many levels I will go down till I finish and make sure that this grammar can generate this string. So it depends on the given string, which is, so here I'm asking you about this one, the parse tree of this string, depending on this grammar. Okay, so based on the string given and based on the grammar I'm given, if this is not exist, I might need more levels of this. If it can fit this string, if cannot, then we'll say that this grammar cannot, or this string is not belong to this grammar. So it depends on the string itself and the grammar I have, then at that time it will give me the levels I know. So there is no rule to know how many levels. Okay. Yep. So there exists, okay. So we said that G1 has a unique parse tree. The derivation of a string W with respect to a grammar G is a sequence of substitutions that yields W. So I don't know how many substitution I have to do, if you mean these by levels. So I don't know how many levels. It depends on the grammar and the given string. It is connected to that grammar. Okay, here, let's have this example. W equal O square, 0 square, or 0 to the power 2, 1 to the power 2 with respect to G1. So we remember that it has 0 as 1 or epsilon. These are the rules. So we will replace 0 as 1, 0, 0 as 1, then 0, 0, epsilon 1, 1 has only one derivation. I don't have multiple options to solve it. Example, if I have 0, 1, 0, 1, so 0 as 1 s, then 0 epsilon 1 s, then 0 1 s, 0 1 0 s 1 s, then 0 1 0 epsilon 1 s, then 0 1 0 s, then I replace this with epsilon, then I'll come back. So you see, with a little bit different string, I have different parse tree. So second derivative, I can do it 0 S1 S 0 S1 0 S1 S 0 1 0 S1 S 0 1 0 1 S 0 1 0 1. So this example, from the same grammar, I can have two derivation, two way to derive the solution. In the exam, use any one of them, whatever you feel comfortable with. So this is just to show you how to make the parse tree. In some string, it might have more than one parse tree. Some of them, they have a unique parse tree. For the level, it depends on the given string and the grammar. Clear, guys? Question till here for the parse tree. Okay, so let's move to the pumping lemma. Pumping lemma for CFL. To show a language is not a CFL, context-free language or context-free grammar. Normally we use L. So a pumping lemma for languages, context-free language or regular languages. Some as to prove that a language is not regular. Something same, but instead of 3 partitions, we have 5 partitions. So here is the same as in the handout. So we ask that L be a CFL and G be a CFG, such that L belong to L of G, let W belong to L, and let T to be the smallest parse tree of W with respect to G. With regards to T, if we start maximize here, how we add V plus 1, the V's. This is not required for you to just to understand, and we explain it. So we have U, V, X, Y, Z. Then V and Y, we can pump them as we show here. So we have U, V, X, Y, Z. Then the length of V, X, Y, and Y is less than D, which is the length of V plus 1. V and Y cannot be empty, both. So same as in the handout as we described. And here we can make like U, V to the power 0, X, Y to the power 0, Y belong to LG. If we replace T2 with T1 here, then we'll have V squared. Here, it's just a step to show you how we can pump V and Y. Just as a clarification here, U, V, V, X, Y, V, X, Y, Y, Z. So here we can have U, V3, X, Y, 3, Z, just to show you an example. Now we will state pumping lemma theorem, pumping lemma for CFL. Let L be a CFL, then there exists P greater than or equal to 0, such that for all W, like the cardinality of W is greater or equal to P. So a partition W, X, V, U, V, X, Y, and Z, where V, X, Y is less than or equal B, and V and Y is greater than 0. And then, so for all I greater or equal to 0, so we should have to prove that U, V to the power I, X, Y to the power I, Z belong to L. So note that P only depends on the CFG that we choose for L. So let's have this example, the one we talk about in the handout. A to the power n, B to the power n, C to the power n, where n is greater or equal to 0. So here is the solution. You should say, given P is greater than or equal to 0, choose W, A to the power P, P, B to the power P, C to the power P. Given a partition W, U, V, X, Y, and Z, such that these things, like it will be a rule, you have to memorize them and write them in your answer. Choose I equals 0. And let Vy equal K. Analyze the string UXZ. So string VXY consists of one symbol. VXY consists only of one symbol, so that VXY consists only of A's. Then here you choose how to choose, like which one with A's, which one with B's, which one with C's. This is your call, how you will partition the string. Okay, then UXZ, A to the power P minus K, B to the power K and C to the power K, U x, z not belong to L, because here we have p to the minus k. And here to the k, here to the k, which means we have less number of A's than B's and C's. And with this case, that this belong to, not belong to the language. If we look to the next case, here how we partition. In the exam, I need from you one case again. Here I'm showing you how many cases, which depends, like I'm trying to predict how the student will separate or partition the string. Vxy has two symbols, and let Vxy consist of A's and B's only. Then Uxz will be A to the power k1, B to the power k2, C to the power p, because the last partition will be C, where k1 plus k2 is less than 2p, U, X, and Z is not belonging to L. Clear? Vxy cannot contain all three symbols, A, B, and C. As Vxy is less than P, so L is not CFL. Example 2, this example. If we have L2 WW, where W belongs to alphabet star, or as in the handout we said, between a bracket is 0 and 1 star, because the alphabet is 0 and 1. Assume the alphabet is A and B. Here we change it instead of 0 and 1 to A and B. So it will be A and B star. Given P greater than 0, choose W, A to the power P, B to the power P, A to the power B, P to the power P. Given a portion of U, V, X, Y, and Z, let Vy equal K greater than 0. In case analysis, also here we'll talk about different cases, how you partition your string again. So suppose V, X, and Y consist of one symbol. Suppose without loss of a generality of Vxy is contained in the first block of A's, choose I equals 0. So U, V to the power 0, Xy to the power 0, Z. Then we'll have A to the power P minus K, B to the power P, A to the power B, B to the power P, which means this one is not equal to this one. So it's not belong to L2. If we take that consists of two symbols, A's and B's. So here the first A's and B's will form the Vx and Y. Choose I equal to, so U, V2, XY2, Z. So it will be AK1, BK2, AP, AP. And where K1 plus K2 is greater than 2P, or it does not have the form of A star, B star, A star, B star. So L2 is not belong to C. So we will stop here today. More examples are coming. Also, with regard to pumping lemma for context-free languages, we'll have also more example in tutorial 2, because it will be part of assignment 2. And also there is a part in the last tutorial which will cover most of the material of the term for the final exam revision. If you have a question, please stay. If you don't have a question, feel free to leave. Have a nice weekend. Have a nice reading week. Next week, no classes because it's a reading week, huh, guys?
Hey, Professor, I just had a quick question.
Okay, yeah.
Could you quickly just go over the first example for pumping lemma for context-free grammar where we had A N, B N, C N? I just didn't catch how it would be A to the power P minus K.
Okay, just a second. Here.
Yeah, yeah.
Okay. Here.
Yeah.
So U, X, and Z, right? Here we pump what? What we are pumping?
V and Y are both being pumped, right?
Yes.
Okay.
So when we choose 0 here, in this case, I think we use 0, right?
Yeah.
Yeah. And we said V, the length of Vy equal to K.
Oh, okay, okay. And so N was VY, like both V and Y are just A's.
Yes.
Okay, okay. They don't, okay, okay.
You got it?
Yeah,
Okay.
I think that makes sense. Yeah,
Yeah.
thank you.
You are welcome. Mahira, do you have a question?
I just have a question about the midterm. If we can know a little bit about the general format.
About the midterm?
Yeah, like if I can, like the general format, is it like multiple choice or is it long answers?
It's mixed format. It's mixed format. So it will be multiple choices, true and false, and some of you written a question.
Okay, and it will cover from handout 1 to handout 6, or will it be beyond that?
No, handout 6 is not part. Yeah, the pushdown automata is not. Context-free grammar is the last. So from handout 1 to handout 5.
Okay. Okay, thank you so much.
If you watch the video of last Thursday or last Wednesday, which is the last 2 YouTubes in the channel, I explained this in details.
I see. I see.
Yeah.
Thank you so much.
You are welcome.
I appreciate it.
Have a nice weekend and happy reading week.
Yeah, same to you. Thank you.
Thank you. Thank you. Bye for now.